Our objective in 4.3 is to evaluate definite integrals as applied to area of regions for the first part of 4.3. To do that, we have to understand what is a Riemann sum. A Riemann sum is defined as a sum of areas of rectangles. Riemann was a mathematician who did his work in this field, and therefore it's named after him. So to remember it, think of R for Riemann, R for rectangles. When we say find a Riemann sum, we are saying find the sum of the areas of the rectangles. And this is what we were doing in 4.2, where we used rectangles to approximate the area between the function and the x-axis on some interval. And we use the symbols of summation, the sum from I equals 1 to n, the first to the nth rectangle, of the areas of the rectangles, which was the height times the width. We could say width times the height, height times the width. It works the same. Now, if we're talking about the areas of rectangles that are being used to approximate the area between the function and the x-axis, well, think about exactly what that means. We were looking last time at curvy functions and saying just on this interval from A to B, we want to approximate this area that's in here. And I can color in that area and approximate it with rectangles. However, if there is a function and perhaps it has some hole. Maybe it has a hole because there's an asymptote. So let's say vertical asymptote in here. And I say, let's find the area on A to B. Well, I can say start at A, no problem. End at B, no problem. I can start coloring between the x-axis and the function, shade it in, shade it in, shade it in. And when do we stop shading? We don't, because there's a gap in there. We have a continuous function here and a non-continuous function here. Can we shade in the area in our non-continuous function? No, there is no area between the function and the x-axis on an interval that is going to be bound. So the Riemann sum is only going to be used for functions that are continuous and also for functions that are non-negative. So let's make a note that f must be continuous. Very important. And must be non-negative. Functions that we dealt with last time, all continuous, all non-negative, we did Riemann sums. But if they are negative, we don't do a Riemann sum. Let's define definite integral. We started the chapter in 4.1 with indefinite integrals. They are different. The definite integral has the integral symbol, but has limits of integration. So we say the integral from a to b of f of x dx, that's what it looks like, equals the limit as n approaches infinity. This is one way to define it. The sum from I equals 1 to n, f of c sub I times delta x. And this is for the function f of x on the interval from a to b. The a and the b, these are called the limits of integration. And notice they come from that interval on a to b. A is the lower limit, b is the upper limit, and therefore we write it a lower to b higher. So remember we said that the Riemann sum has to be continuous, has to be non-negative. But in a definite integral, we don't necessarily have that non-negative restriction. Notice this part of the definite integral definition looks very similar to how we showed the Riemann sum in the symbols. I'd like you to sit back and just look at this next scenario. This is not in your notes. I just want you to check out this next scenario. So just sit back, listen, and soak up this information and try to understand where these symbols are going to take us. So we said, just to have it to look at here, the definite integral, what it is, integral on a to b of f of x dx, and how that equals the limit of the sum of f of c sub I times delta x from 1 to infinity, and then, oops, I'm sorry, not infinity, that's n is going to infinity. And we said that this part is how we symbolize a Riemann sum. So if we are spending some time talking about areas and spending some time talking about how functions can't be negative to use a Riemann sum, let's check out a function that is partially negative on some intervals. So this parabola, I'm going to sketch a rough graph of it. So the vertex is down 2 units, so we'll put its vertex, try to get a decent sketch of approximately what that looks like, and only on the interval from 0 up to 2, so it's approximately like this. And I'm going to shade between the function and the x-axis, like we've been discussing for the Riemann sum. So I'm just shading approximately on 0 to 2 between the function and the x-axis. This is the area that we would say we'd want to find if I were looking for the area between the function and the x-axis. So let's say we're just to use rectangles to estimate this area. And maybe we don't use too many rectangles just so we can see the basics of this. So let's say I'm going to split this region up into a couple rectangles, and I'll divide it up into 2 subintervals, and maybe I'll do one rectangle over here. So and we'll just take about this region right here. Now, if we use right endpoints, like we focused mostly on last time, I'm going to look at this first subinterval, and it has a width, a positive amount, some delta x amount, and looking at a right endpoint, I'd go to the right side of the subinterval, and notice that I have to go down to the function. I have to go down to the function, which means if I'm literally using f of x to find the height of the rectangle, this f of x value is in the negative direction on the y-axis, so that's a negative value right there. So if I'm finding the area of the first rectangle, that f of x value that I'm using from my function is a negative value, a negative number times delta x. Well, delta x is a positive number. So why am I calling this area? Area is not going to be negative, but yet I have to say the f value times delta x, the height of the rectangle times the width. Well, I'm not going to call that area. That doesn't make sense. That's a negative number. Over here, where I have positive, on the right side, I go up to the function. That's a positive value. So for that one, let's call that my second area. That's going to be a positive f of x value n times a width. That difference between those x values, that's always positive. So times a positive. So that would make sense to call it area. But for the part that's below, my function value is negative. And if I multiply my negative value times my positive delta x, I get a negative value for area, and that doesn't make sense. So if the definition of a Riemann sum is a sum of the areas of the rectangles, we only are using a Riemann sum when the function is non-negative. But what does that mean about definite integrals if there is no restriction? There's no restriction on a definite integral being non-negative. So let's take this to the definite integral scenario. Get rid of the fact that that looks like a Riemann sum. If I'm literally just using the f of x and the delta x, this part over here is going to give me negative values. All of that area is going to give me negative values if I use the f of x from the function. This part over here is going to give me positive values because the f of x is positive. So if I'm literally using the f of x values in my sum of f of x times delta x, the part below the x-axis will be negative, the part above will be positive. So the way we describe the definite integral then is not by calling it Riemann sum, not by calling it area, but by calling it the net area. The definite integral is the area bound by the curve of the function that's above the x-axis minus the area below the x-axis. Let's say this area gave me approximately, let's say it's approximately some positive value. Let's say it's about 3 square units of area. Let's say that down there, because of the function values, gave me a value that's approximately -4. And I'm not going to call it square units because that doesn't make sense. Area is not negative values. But if I put these numbers together to say what is the area, I would say, well, this has an area of 3 square units. This has an area of 4 square units. So the -4 is a representation of the fact that it's below the x-axis. So I've got my area that's above, let's say it's approximately 3 square units. The area that's below, let's say the way it's drawn, I'm estimating approximately 4 square units. Because this is below the x-axis, because I'm getting negative function values, it's actually the area above minus the area below if I'm using the function values. So I'm not saying that my area is -1 square units. I'm saying the net area, the difference between the areas. The definite integral represents, now this will take down in your notes, the net area. That is the area above the x-axis bound by the function and the x-axis minus the area below the x-axis. Okay, the net area, subtracting what's above minus what's below. Because of the way the definition is written, if we're using function values, the function values below the x-axis will be negative. One final note we should take about continuity and integrability is continuity. If we have a continuous function, we will be able to find some sort of area. Continuity implies integrability. If a function is continuous, we will be able to integrate.